Hello and welcome back to my infrared YouTube channel. According to my roadmap, I will show you, in each video I will show you a new application of infrared, and over time they will become more and more astronomical. But for today I want to show you near-infrared spectroscopy, in short NIRS, as an application especially for medicine and brain science. So what is NIRS? NIRS is a form of spectroscopy that uses near-infrared, but not only near-infrared, but also slow-wave infrared. So it works from 760 to up to 2500 nanometers, as you can see in this example of a spectrum here. And people use this kind of machines, and it's quite a difficult form of spectroscopy as compared to spectroscopy in the visual, because often you have wide spectral lines that are overlapping, so you have to statistically separate them. You can't just have a look and say, oh, there's of this chemical and of this chemical. But the interesting thing about it is you can look at molecules. In the industry, people often use calibrated spectra, and then they look at deviations from this calibrated spectrum. For example, they can compare dry and wet samples from each other. So often it can be used to see if things are still fresh or not. But it tends to be detective work, and this is even more true for spectra in the longer wavelength infrared. Typical applications are to look at water contents, food quality, or you can separate different sorts of plastics with near-infrared spectroscopy. Later somebody found out that you can use it in medicine because you can look at tissue oxygenation. First, actually, people use this cytochrome oxidase that is involved in energy metabolism. So in producing ATP, which is the most important energy molecule in the body, that can be synthesized from ADP plus a phosphate. But later this molecule became more used, which is hemoglobin. Hemoglobin is the way of the blood to transport oxygen to the mitochondria, these little cell organelles here that are everywhere where the body needs energy, because they can do oxygenation, which is aerobic breathing. But somehow the oxygen has to come into the body, which doesn't work by passive transport. You need a molecule that binds it and then releases it close to where it's used in its mitochondria. So hemoglobin is a tetramer made out of 4 different proteins, and it contains iron. That's why it's rusty colored. And the interesting thing about this molecule is its absorption rate is different in longer and shorter wavelengths, depending on if it's carrying oxygen, which means it's oxygenated, or it doesn't carry oxygen. And then people calculate the ratio between oxygenated and non-oxygenated hemoglobin. Because especially in medicine, if people are lying on a bed and they have lots of deoxygenated hemoglobin, this is not a good sign. When they're doing sports, of course, there may be deoxygenated hemoglobin, but then more oxygenated hemoglobin will come after in the body. And this is something that happens also in the brain, as we will see shortly. And in this optical window, there is on one side more absorption in the non-oxygenated hemoglobin, and on the other side it's the other way around. So you can just compare along this line of 800 nanometers, you can compare the absorption, and then you can tell if the blood tends to be more oxygenated or more deoxygenated. These can be used in anesthesia. If you had an operation already, you know that you get this little thing on your finger, which is to measure oxygen in the blood in the finger. But in heart operations, of course, it's for example, it's important to see if there's also oxygen in the brain still coming, despite a heart being out of work and replaced by a pump or something. So people do that with a lot of sensors on the brain and light sources also on the brain, and then you can measure these RSO2, which means the relationship between oxygenated and non-oxygenated hemoglobin in the brain. And people also do it in infants a lot. And here they just take one sensor on the forehead and measure the relationship between oxygenated and non-oxygenated hemoglobin. Why is that possibly enough? There are 3 large arteries going to the brain, and here I assume they put the sensor here because it's in the middle between 2 of these arteries. So if there's enough blood here, you can more or less conclude there's enough blood in the whole brain, because it's a part of the brain that is the part of the brain that is hardest to supply with blood. Then in brain science, partly also in therapy, you could use NIRS like this. Here you see a big cap with a lot of sensors, or here also. You can monitor if people are doing certain things, how the brain reacts. Similar to functional MRI, but the good thing is the person can walk around and it's quiet compared to MRI, which is a relatively loud method. The main disadvantage is you reach only about 1 centimeter from the skull. So you can measure neocortex in most cases, but not deeper structures. And you may have some problems if brains are atrophied. You may not reach the cortex anymore if there's too much space between the skull and the brain. There are many different types I won't mention here. The most common type is continuous wave NIRS, which is what you would expect. Just you put the light into the brain all the time and measure all the time. And then you can make maps like this and compare, for example, if somebody did a training or if somebody did not a training, if there are differences that are color-coded here in these parts of the brain. NIRS has also been used to try to answer old questions. For example, what happens with the blood if people are using their brain? Normally, blood tends to get deoxygenated a little bit in the beginning, and then there's this positive response where lots of fresh blood are supplied. and I mean a lot more than you actually use to replace the oxygen used here upon this work that the brain did. And this is still not fully understood why so much blood comes in a relatively wide area of the brain. People have to try to investigate this initial dip and what does it mean? Is it always there? And is it more accurate than this response in measuring? Especially when it comes to where in the brain something is happening. And there are some studies made with NIRS that tried to understand this reaction more. For example, then you can look at oxygenated and deoxygenated hemoglobin separately. So what comes afterwards is the red line is a lot of oxygenated hemoglobin. And this dip is very interesting for science, and it could also be used maybe for brain-computer interfaces. So people have the ability to steer a computer directly without using hands or eye blinks or something, which is not only interesting for science but could also be important for certain patients who are completely paralyzed. NIRS can also be used for therapy, for example for migraine or certain diseases that you could influence by the brain, but people don't know how. So the principle is just you measure something from the brain, either EEG, electroencephalogram signal or signal based on NIRS, feed it into a computer and show the person the success of the intervention, of the trying on a screen. So people can learn to improve certain conditions by steering their brain. The hard thing is you can't tell them from the beginning what they should do. They have to figure out that themselves, which is the hard part, of course. But as soon as you find something that improves the condition, they can see it on the screen. Sometimes it's enough to change the breathing pattern or things like that. May also be easier than use EEG, but there are more studies needed for that. Now, thanks a lot for the attention. Here on the image you can see how white light becomes red when you shine it through a hand, for example, and this is probably also due to the hemoglobin in the hand. Bye bye for today.